In this problem, we're going to look at an example of determining the flow rate, which is a problem of the second kind. In this example, we're going to look at air at 1 atmosphere that's transported through a 300-meter long section of duct with a given diameter, and this is the diameter of the duct that we determined in the previous problem where we looked at what was the diameter that was required for a given head loss. So for this problem, we're assuming that the head loss is going to remain constant at 20 meters, and we want to determine the flow rate of the air through the duct. So in order to do this, again, we're going to start by writing all of the variables that we know in the problem and determining what it is that we're trying to find. And in this case, we're trying to find the volume flow rate of the fluid. All right, we also know that it's a plastic pipe, therefore our surface roughness is approximately 0, which is based upon looking it up in the charts, and we know that a plastic pipe is very smooth and has a low roughness associated with it. And in this case, we're given the head loss value that we want it to be 20 meters, and we don't know what the velocity or the flow rate needs to be to make all of these conditions true. So again, we know that we can determine the average velocity of the fluid based upon the volumetric flow rate, and that's related to the pipe diameter. Again, in this equation right here, we don't know what the volumetric flow rate is, so that's one of the parameters that we're going to determine. To determine that, we're going to need to know the Reynolds number to know whether we're in laminar or turbulent flow, and that's going to help us calculate the head loss. But remember that this is based upon the Reynolds number, and the the Reynolds number, which is based upon the average velocity, depends upon the volume flow rate, which we don't know yet. We know that we want the head loss to be 20 meters, and according to the Darcy equation, we can determine the head loss if we know the friction factor here. Based upon the friction factor, our equation for the friction factor is based upon the Moody chart, and the Colebrook equation is a mathematical representation of the Moody chart. So again, we need to determine this friction factor, and this friction factor depends upon the Reynolds number, which depends upon this volume flow rate, which we do not know yet. So again, we have a system of equations where we're going to have to use a guess and check method to come up with an iteration process to guess what this value is that's going to satisfy all of these other equations, both the Colebrook equation as well as our head loss equation. So moving over to Excel, again, I'm going to enter all of the information that I know. And again, I don't know in this case what the volume flow rate is. So I've made all of my calculations, all of my parameters that I've calculated change based upon this volume flow rate. And the volume flow rate that we determined previously was, let's see, where was that? The volume flow rate that we determined in the previous one, or sorry, that was used in the previous question, was about 0.35. So I'm just going to set it to that right now. And I've used that value to calculate the Reynolds number as well as this Colebrook equation and our head loss. We see that based upon that guess of 0.35 cubic meters per second, our head loss is going to be about 33 meters. And our Colebrook equation, the friction factor is wrong because the Colebrook equation is not being satisfied in that our squared difference is non-zero. So what I'm going to do is guess some different values of the volume flow rate here to get it approximately close to our our desired 20 meters of head loss. And then I'm going to use the solver equation to help us hone in on the best value for the volume flow rate while adjusting the friction factor to meet the requirements of the Colebrook equation. So here's how it's going to work. I'm going to guess that since we have a high head loss here, that our volume flow rate should be lower to reduce that head loss. So I'm going to guess, let's go to 0.3 and see what happens. So that reduced the head loss to about 25. And let's see, I want to get closer to 20, so I should go down to maybe 0.25 cubic meters. And that gets us a head loss of 17 meters, which is pretty close, so maybe I should bump it up to about 0.26 cubic meters per second, maybe to 0.27. There we go. So 0.27 gives us 20 meters of head loss. Of course, I have not yet adjusted the friction factor. So I'm going to let Excel do that now and get our square difference for our friction factor down to a value of 0. It's at 1 right now, so it's pretty close already. The reason that I want to adjust my value so that I'm close to my desired objective value, which is a head loss of 20 meters, is so that Solver can find the solution. If we're very far away from the solution, it's not going to be able to converge to a solution because it's using basically a Newton iteration technique. And if it's not close to the correct solution, it may go off in the wrong direction and not be able to actually solve the problem. Alright, so now that I have my volume flow rate at something that's going to give me a head loss of about 20 meters, I'm going to click on my head loss calculation and then open up Solver. Solver, I want to again set my objective to be the head loss, and I'm going to set that to a value of 20. Now in Excel, I'm going to allow the Solver tool to change the volume flow rate and the friction factor. And I have to set the constraint that the friction factor is, when it adjusts the volume flow rate and the friction factor, the square difference between the right-hand side and the left-hand side of the Colebrook equation must be identically 0. So I have my objective, the variables that Excel is allowed to change, or that Solver tool is allowed to change, as well as constraining the Colebrook equation to work out. Both the right-hand side and the left-hand side must have the same value. So now that I have all of those entered, I should click Solve, and it says Solver found a solution. The solution gives me a head loss of 20 meters. It satisfies the Colebrook equation because the square difference is very, very tiny here. It's almost 0. And it converged to a solution where the volume flow rate was 0.237 cubic meters per second. So that's the final result here that was obtained by using the iterative technique in the Solver tool to come up with the best solution that satisfies all of the equations that we wrote down.